Uh, Today I'm doing something different. I've been looking into quantum computers and they've really sparked my interest. I think it's a very interesting field, and probably we are going to be all doing quantum computation in the near future, and we already are. But it's not as widespread as classical computation. But it's worth noting and understanding how these things work. Just to illustrate that um, there are some considerable things going on in this field. There is already 100 plus qubits computers that you can access and run your algorithms on from IBM and Google. And recently, Microsoft has also released their own version of quantum computation. I'd say not an exactly a quantum computer, but they have released a system through which you can build a large scale computer. And these things deal with errors, and they're very they are known for the notorious errors that they contain, because a qubit essentially is, if you could look at it as a photon or some kind of energy state. These kinds of things cannot be really held constant for a long time, because the environment really affects their behavior. So even just a little magnetic field from the solar flares could really affect it, or some people breathing, or even a temperature change or anything like that could really affect it. So because of these things, the problem with quantum computation and essentially quantum computers is that the errors have to be mitigated somehow. And so that's another topic for another day. But what I'd like to focus on today is Simon's algorithm. You see, Simon's algorithm is really an explanation of how quantum computation can be utilized for a computation that is essentially reducing an exponential complexity of solving of computation to a complexity of n. So now let's say you have like 1,000 qubits, then it would scale exponentially 1,000, right? But if you do it through the Simon's algorithm, then you'd only have to calculate the 100 qubits. That is much easier. And then considering that the calculations of quantum computation deals with tensors mostly, because we are dealing with complex spaces, and these spaces are really they kind of increase in complexity as you increase the qubit. So let's say you have a single qubit and you'd like to apply an identity gate, right, or something like that. Then you'd have only a 2 by 2 matrix, right? But if you have a 2 qubit, now you'd need a 4 by 4 matrix, because now the space that the space that contains the qubit has now expanded. So let's say the classical qubit can contain 0 or 1, and this remains the case for the every individual bit. But when you come into the classical ones, there is a process of entanglement and the process of like mixed states and pure states. And so what happens is that having multiple such qubits or registers, these spaces actually interact with each other, and now we need some other space to represent this. And so algebraically, or like linearly, because these are governed by linear equations, we need to have spaces that can contain such kind of qubits. So because of these problems, the calculations grow exponentially, and solving tensors exponentially is really taxing on computers, at least of current times. So let me start with this. Of course, you need some kind of basic information about quantum computation first. But it would be really a big challenge to carry that out right now. I think you should have some information about it. You should have gone through Dutch Joza, and even Barsin Wazirani to understand what's going on in algorithms. In Simon's algorithm. So let me start with the basic problem that the Simon algorithm proposes to solve. So here's Simon just sitting one day, and he decides that what would I do if I had a function that would give me the same output for two different inputs, and how would I know by which mechanism it gives me that kind of output, right? So he calls that mechanism the secret string S, and he says that inside of the black box there is a system where it's taking the input, right, and it's just doing something with it, with the secret string, and we get some kind of output that contains the information about the secret string essentially, right? And so the problem is that we need to find what's the secret string S. We don't know what it is. We are not told. This is a black box, this is an oracle, and based on the outputs and the inputs we give it, we should be able to identify what kind of secret string is embedded in here. So a string, since we're dealing with binary numbers here, let's say that you have let's say you have a function of x, let's say x plus 1, right? And this would be your input, and this would be the part that is affecting the output essentially, and you feed it f of 1, this gives you 2, then you feed it f of 2, that gives you 3. And so you can probably see from here the pattern that there is something that is being added to this input, and you see the and you just conclude that it is actually this part, which is 1, and you call this a secret string S, right? That's essentially what's going on in Simon's algorithm. So now that we know the problem, there's a special kind of vocabulary that goes in here. There's a special kind of function that it can take. It cannot take any kind of function. So a special kind of function will work with this algorithm, and that special kind of function is something that is 2 to 1. So a function that is 2 to 1. So it is a function that maps a set of n qubits. So this set can be expanded as this. So each qubit contains n equal superposition of 0 and 1, or just a set elements of 0 and 1. And when you have n of these, that means that you have n qubits tensored with each other, right? And this gives you some kind of a state such as this. Say we say that n equals to 2, then this would be let me see, this would be 0 0 plus 0 1 plus 1 0 plus 1 1. And you'd know from here that all of these are in equal superposition, right? And so this is what I was trying to get at. Now let's say that you have such a system. Let me get rid of this. So this function essentially has to map a set of n strings. So n bit or n qubit input to a set that has m qubit outputs, right? So say you give it like 1 1 0. This could give you 1 1 1. That is the same number of qubits, or it could give you 1 1 0, and it could give you 2. So that would be the case where m is not equal to n, right? And this is the case where m is equal to n. But we're going to be focusing only on this part and not this part, right? So now you might be asking, what kind of functions are there that would give us this kind of behavior? So I could just make up a function right now that should have this property and this property. Let me try it for a 2-qubit version. So let's say x is 0 0, so these can be read as 0 1 2 3 in integers, right? And in binary it's 0 1 1 0 1 1, right? And then f of x would be, let's say this gives you 0 0. Let's not make it 0 0, let's make it one of the 4 possible states, right? It has to be one of the 4 possible states. And because you know, space of qubits that sorry, a complex space of complex space that contains n qubits has to contain all the possibilities, right, that the n qubits in tensor form has, you know. So like 2 qubits can generate like 4 states, right, that are in equal superposition, and then 3 qubits would create like 8 states, right? So it goes on like this. So the output has to be one of these or more, right? So let's say I get 1 1 here, and then I get 0 1 here, and then I get 1 1 again, and then I get 0 1 again. Now you'd see that I'm getting here 1 1 here and 1 1 here, right? And these are my 2 inputs. So this essentially has become a 2-to-1 function because we're giving it 2 inputs and we're getting the same output. Now here's what's interesting about Simon's algorithm. If you were to make this, you know, let's say 1 1 0, right, then this would not fulfill the promise of Simon's algorithm. So this would not work in the Simon's algorithm, because this is also a part of it where it's saying that the whole function has to be 2-to-1, right? So it's not just some inputs that have the same output. All of the inputs must have 2 inputs and the same output. So let's say you have an n qubit where n equals to 2, right? It could generate 4 states. Then we would automatically have 2 duplicate states that are distinct, but yet they are duplicate, you know, they are the same. So in what case would this work? This would work in exactly this case where we have this 0 1 here, right? Now this and this are the same, so we have 0 1 and 1 1 here, right? So we could say that the set of 0 0 and let's say 0 0 and 1 0, this maps to give us 1 1, and the set of let's say I mean we can see it right here, 0 1 and 1 1, this gives us the set of 0 1. Now this has become a 2-to-1 function, and this qualifies because we have m qubits here and n qubits here, and if you see here we have 2 qubits here, 2 qubits here, so it takes n qubits and converts it to m qubits where n equals to m. Now let's say, so we haven't yet explored the whole promise part of the Simon's algorithm and what it's trying to say, because this is really important. The whole of algorithm lies in what he's trying to do. So think of it like this: the guy has just, you know, been sitting in some room and he decides, this is my game, and these are my rules, and this is how I want my players to play. Whether that game makes sense or not, is logical or not, well, I mean, this has to be logical. Simon's was a great man, I'm sure, but so this is his own playground. He likes to create things as he wishes, so we have to play by his rules. So he says that you know, our f of x will equal to f of y, right, if and only if you know, if and only if, now talking about the inputs, x is equal to y, or y is equal to x XORed with s equals to y. Now here's an interesting part. So our inputs, let me just copy this here. Our inputs here, as you see, are exactly 2 to 1, and we have to check whether our f of x is equal to f of y. So our x1 is going to be 0 0, whereas x2 is going to be x2 is going to be what? So we have to pick the ones with the same output, so it's going to be 1 0. Now for the function to fulfill the promise, or the requirements at least, it has to be that so this is our x and this is going to be y, so we could call this y, right? And we would say that, of course, this is the trivial case where both of the inputs are the same. It would give you the same output, right, which is 1 1 in this case. But let's try XORing with s, right? So let's say your s is unknown. Now how would you find the s? Now this is where another rule of Simon's problem comes in. So he says that for a 2 to 1 function which follows all of these things that I've just mentioned, have to it has to, absolutely has to, have the proper property of having the two having the two inputs which are generating the same output. When they are XORed with each other, we get the secret string s. Now this is one way how you could get the string s, but there are other ways as well when we do it quantum mechanically, and I'm going to show you that later on. But x mod XORed with x2 gives you s, and this secret string s has to be only one in this whole function. So I cannot say that when my f of x is going to be x plus 1, right, and for x of 2 this becomes x plus 2, right? These two are not the same, so these functions will not behave the same. So we are saying that for the Simon function to work, this secret string s has to be unique, has to be non-repeating, it has to be distinct and non-repeating. So this is one property of it. Now let's say you have s, right, and so it says that for the function to be implementing the Simon's algorithm, it has to have f of x equal to f of y if and only if our x equals to y, or y XORed with x XORed with s gives you the y. So in two of these cases, now I'm going to demonstrate how this works. So let's find the secret string here. So our same output is going to be this one, 1 1 and 1 1, right? And now let me take the input and XOR them with each other. So 0 0 and XORed with 1 0, right? This XORed with this, and this XORed with this, right? We know the rules that 1 XORed 0 or 0 XORed with 1 both give you 1, and 0 XORed 0 or 1 XORed 1 both give you 0. In that case, we would see that this gives us 1 and this gives us 0. So our secret string is 1 0, and you could do it in a short way by saying that whenever we XOR some value with 0, it basically becomes the value which has something other than the 0 value, right? So if I do 0 XOR b, then we have b, right? We could do it simply like that. So we have the secret string, right? Now let's first confirm that we are indeed getting f of x equals to f of y, where y is basically x mod secret string s. Now let me see. So let's say our f of 0 0 gives us 1 1, which is basically f of y, which is equal to f of 1 0, right? 1 0 generates 1 1, 1 0 generates 1 1, and 0 0 generates 1 1, and we say this is f of x, this is f of y. Now let's check whether f of x is equivalent to f of x XORed with s, right? Because we know that this should generate the y value, or in our case the next value would generate the same output, right? So let me say that this is f of x should be 0 0, and then f of x, so 0 0 mod, right? Because these are the same values, right? They haven't yet incremented or anything. And secret string is going to be 1 0, right? You know that this gives us 1 0, and so the function becomes this, and so we get f of 1 0, and we actually see that f of 1 0 is indeed 1 1. So now we have cleared another concept, that these things have to be true as well, right? So so let's say now that we have done the promise part and what the Simon algorithm is actually doing, how do we actually go about doing this, right? So I'm wondering whether I should take you with mathematics first, and then the diagrams and things like that. But I think I'm just going to show you the circuit first, which is a bit overwhelming, but stick with me. So this is the kind of basic circuitry that it proposes, that can tell you the properties that the Simon's algorithm is trying to define. So the Simon's algorithm will, in this case, tell you what the secret string embedded within this function, within this block, is actually, right? So the way this works is that we have a qubit in 0 state, so n 0 qubit states in the first register, and then we have another 0 string of of n size in the other register, right? We call this R1, we call this R2. And what happens is that we are initializing these with 0 because there's a special reason for it, and I'm going to tell you that in a bit later, right? So what we do is that we first introduce the Hadamard gate here, where it creates a superposition state of each, and we know that generating a superposition state of H gives you an equal superposition of 0 gives you a 0 and a 1 in equal superposition. So we also call that X state, plus state. So we have 3 plus states in tensor form. So when you expand that, then an easier way to remember this is then this has become 0n, where n becomes 3, right? Because these are 3s. So now you have to think, what are the possible inputs? What are the possibilities of a 3 qubit register? And in the case of 2 qubits, you know that it is 0, 1, 2, and 3 in qubits form, or we could write it generally as 2n minus 1. Oops, not like that. 2n minus 1, right? So it contains 4, and then minus 1 becomes 3, right? So this contains 4 states which are numbered as it's shown here, and so a 3 qubit state would contain a 3 qubit register would contain 8 minus 1, this would be 7 states, right? So you have to write the 7 states in a tensor form, and then you have to have it in equal summation of each state being in equal probability of occurring, right? And so we do that by normalizing, and you know this stuff. But I want to highlight why we have this R2 here. If you know about Dutch Joza and Dutch, we know that we didn't have the R2 here, and this is something new. We have R2 here because we ultimately want to write whatever is happening in this function to these output states. Why? It's not clear to you right now, but I'm going to explain. And this can be explained with mathematics. And here I have, so let me just complete this explanation of the circuit. And so what's happening here is that we again apply Hadamard's, collapsing the superposition, and then measuring only these three outputs. Now, why do we do this? There's a very simple answer, right? Very simple answer. If you would like to see, we also measure this, but it's not seen usually. So once we measure this, consider this to be f of x, right? Because whatever is happening here is transferred to the bottom registers, right? So this contains the memory of x, which are this register. This is our x, right? And this register contains f of x, what's happening in this function, and then writing that in here. So once that function is written and we measure this function, now this other function, which is our input, must correspond to the value of x, right? So we ultimately want to find out which x's are producing the functions, right? And this would align with the fact that Simon's promise tells you that x and x XORed with s gives you the second input, right? So if we know about the inputs, we can confirm whether this function satisfies the promise and what the secret string is, right? But I'm going to explain this a bit more later on. So this is what's happening in the circuit. Now let's jump into the mathematics. This might be a bit interesting or boring to you, but I have a great paper here from Hafiz Muhammad Ali Mullah. He is from LUMS, and he has created an awesome write-up on Simon's algorithm. So he's explaining what kind of a problem it is in introduction and things of that sort. And here he is explaining the 2-to-1 and 1-to-1 functions. And see, it's also mentioning here that x1 mod x2 gives you b, which is he's representing b as a secret string s, right? So now here he has written the same thing, but now he is measuring it here. Now in some tutorials you will see this, in some others you won't. I'm sure this has to be mentioned because apart from doing this, you can't get the answer, right? So going a bit further, now it explains so what we are actually getting, right? So let's see. So in our first stage, so let me just show you, right? Consider this to be our first stage, 0, which contains n qubits, and then 0, which contains n qubits, right? Applies u of f, then a Hadamard, and before it a Hadamard of size n, of size n, and then measuring this through some way or another, and you get a classical bit out, right? But you don't measure this in some usual write-ups, but you do have to measure this. So I'm just going to write it here. Please correct me if I'm wrong about this for the people that are actually experienced with this. Now let me write this like this. So this will be a psi1, this state at this position, at this time I should say, it's psi2. This at this time is going to be psi3, and this going to be psi4, right? because after this does not remain a quantum state, so we do not show this as a psi, right? So I'm going to put this here, and I'm going to put this right here. Right, now I think it makes a bit more sense, right? So it's saying that psi1 is going to be this state, which is a tensor product of both of these. Now, those of you familiar with such calculation, this will make sense to you. If this doesn't, you have to go back to the basics. And now what happens when you apply Hadamard to n states? Well, you create an equal superposition of them, right? As you can notice that nothing has happened to this second register, right? Now here's a bit of a difference with the notation. Qiskit, which we are going to be using for programming this, usually uses the rightmost position for the topmost qubit, right? So that is actually the the qubit that it's using. But usually what happens is that in calculations we use the rightmost qubit to show the bottom qubit and the leftmost to show the topmost qubit, right? So as you see, now we are summing over the x state, and whereas the x's are supposed to be 0 1 1 0 0 0, things like that, right? So when these expand, I'll show you the output later. And what happens later on, that you get a psi3, right here you get a psi3, and in this place what's happening is that now the information has been processed and a function has generated some output, and that output is now written in here. Now how does it actually do? I can just show you right now. So let's say this is 0 and this is also 0, right? If you have a C0 gate here, let's say, right, you have a C0 gate here, and you know about C0 that this is a controlled part and this is the target part. If this is 0, the answer is 0. So if we are measuring this, right, if we are measuring, because see there's no information here, so I'm just going to call this B, right? We use this as the ancillary qubit, so we do not use this qubit for further calculations. And so what happens is that if this is 0, then C0 will not be activated, and the X gate here will not apply to this one. So you get B equal to 0. See, this information is now copied onto this qubit. Now you might know that cloning is not possible. This is not cloning, right? This is not cloning. And then if our state is 1 and not 0, now this is going to be activated, and this function and this qubit the X gate will now act on this 0 state, making it 1, because you know that X0 is going to be 1, right? And so we get B equals to 1, right, when you measure classically. So not even classically, because I mean you get the probability amplitudes for it, but let's say you get a state 1 and you get a state 0, right, of like 100% probability of some sort. So this is how you transfer the information here. Oh, sorry, I coughed there. Okay, so what happens with psi3? Now we have this state where the information has now come into the second register, right? And this register is not touched yet because we have already applied the Hadamard gates here, right? And we go down, and now what we do is that we measure this function here, this register here. If you remember, this register contained f of x, right? And you know that this f of x was in superposition of x that belonged to 0 and 1 states, right? So this would contain all of the possible f of x's, right? So what happens when we measure this, right? Of course, the state collapses to contain only the part, excluding this, all of the part excluding this state. So essentially what it will contain is the inputs that corresponds to f of x. Now f of x could be anything. Let's say I measure 1 1, right? Then of course it should contain the x being 1 1, right? Because if x is 1 1 here, then f of 1 1 will be encoded right here. Otherwise there is no way, right? And if this x is in an equal superposition of multiple states, so let's say 1 0 1 1 1 1, right, then we get a function that is based on x that also contains all of the corresponding outputs, right? If that makes sense. I'm sure you'd need some time to grasp this, so I recommend you read this very nice document, and it will make things clear a bit. Right now we get two possibilities here. Either when you read this and the state collapses to contain only the inputs, you could get such a state, right, where we get an x and a y in equal superposition. That means essentially that our x will generate the f of x that we just read, and our y is also going to generate the f of x we have just read in equal superposition, so like in equal probabilities, right? So we also know that y can be expanded as x XORed with s, or x XORed with b, right? So we write it as such right here, right? So now what happens is we know that if we apply the Hadamard gate again to the first register, so on this register, right, this whole register, what happens is that now this generates further superposition states, because you know that x belongs to a set of n qubits, where the numbers are represented as binaries. So if my x, let's say my x is going to be 0 1, right? Let's not call it even 0 1. Yeah, let's just call it 0 1. Then applying Hadamard on this, right, x should now give us the same superposition, where this is now donated with z, because for each x is going to generate further states, right? But a difference here is that for the basis states, where we have measured this with 0 or 1, right, that created a defined state where the signs or the negative or the positive amplitudes were always the same, right? So we didn't need a global phase to be evaluated here. But now, because this is a superposition state, we get a possibility that we might get, for example, minus 1 1 instead of 1 1, right? So we need to include this possibility, and that can be done with minus 1, where this is evaluated as x dot z, right? Now this is a bitwise dot, right? And what happens is that, but this is just not just any dot. Let's say we have 1 1 and we have z to be 1 1, right? But this is not just dot, this is a modulo 2 dot, right? So this will either evaluate to 0 or 1. And solving this, 1 to 1 is 1, right? Mod, 1 into 1 is 1. And you know that 1 into 1 is going to be, sorry, 1 mod 1 is becoming 0, and 0 modulo 2, sorry, I should put the modulo sign here, and this becomes 0 again, because there is no remainder, right? 0 is just this, right? So we get minus 1 to the power 0. This is just positive 1. So the amplitude, right, the amplitude corresponding to the input x, which gave us our f of x, is now in positive term, right? So this is a constructive interference. But when we have a negative sign, then that's a destructive interference, right? I mean, you'd have to do the calculation to see where it's destructive and constructive, but we get an alternating sign of this sort. So we add this minus 1, and then we add the z here, because it's going to generate the states actually, right? So this is essentially what's happening here. And if you apply header mod to x, right, this would give you a phase where it's evaluated by x dot z. Let me just zoom that in a bit. Can I? I don't think so. Can I? I don't think so, but what's written here is x dot z, and when we apply the header mod to this state, because these both belong to the same register, so header mod will be applied on both of these, we get y dot z. Now y dot z, again we are assigning it different superscripts here, because x could be 0 1 and x mod b could be 1 0, as we saw earlier, right? They both give you the same output, but inherently these two inputs have to be different to become a 2 to 1 function, right? So we get a y dot z here. So both of these generate an equal superposition of the states that are contained in the space of n qubits, right? So the output is going to be common to both of these. So right, it's going to contain z outputs. Now what you're going to get here is some sort of unequal superposition of 0 1 plus 1 0, minus 1 1, or plus 0 0, or things like that, right? An equal superposition of them, right? Because of this part. So now what we do is that we have the z's, so basically our outputs. This is what we see when we measure them. Here now we have to do some more mathematics. We understand that x dot z has to be equal to y dot z. Why? Because if you see here, these two amplitudes, they will add constructively when they are the same. So it could either be -1 plus -1. If both of these are raised to the power 0, then you get -1 plus 1 plus 1, that's equal to 2. That's constructive interference, right? And you could also get this to be 0, right, because of destructive interference, by having x dot z not equal to y dot z, right? Now we simplify this system by doing some mathematical magic here. So x dot z is equal to x XORed with b, because y was equal to XORed b, and then z remains the same, right? And then by the rule of multiplication with an XOR, we know that it distributes, so we get an x dot z XORed with b dot z, right? And so when we cancel x dot z from both sides, this can be done by XORing on both sides with x dot z here, right? So you get a same thing. So a XORed with a is always going to be 0. We know this because of 1 XORed 1 equals to 0, and 0 XORed 0 equals to 0, right? So x dot z with XOR x dot z is going to be 0. So what's happening is now only b dot z remains, and that equals to 0. Now the operation that we do here is going to be mod 2. So whatever calculations we do to find b dot z, it has to be a mod 2. So if we do a binary multiplication, that multiplication cannot just be 1 multiplied by 1 plus 1 multiplied by 2, right? This becomes 3, right? So 3 would mean nothing in the world of binary. You essentially have to divide that by 2 to get either 0 or 1 to get a binary data, right? So we get this kind of output. So now we know that once we run it, we get a certain z, and we know that b dot z has to be 0 for the condition that x dot z equals to y dot z, meaning that our function was essentially 2 to 1, and that the amplitudes add constructively, right? There are many other postulates that can be derived from these results, but this is what we have right now. Now, this was just for a single run, right? This was just for a single run. Say we have n run here, so k run here. So we turn on the circuit, we switch on the light bulb, and we feed the oracle these inputs, and we measure them once, twice, thrice, things like that, and we measure it like 10 times. So we get Z1 ranging from 1 to 10, right? And what you would get is you'd get a system of linear equations, and such linear equations have a name, right? These equations are corresponding to null spaces. So in order to calculate B, you'd have to find the null space of the matrix Z, right? So the matrix Z is going to be anything like this, and this multiplied with some vector is going to give you 0. We essentially have to find this vector called B, where multiplying this with the matrix Z, right, we would get 0. And you know, how you make sense of this is going to be different for everybody. How I make sense of this is that we have to find B, a certain B, that is orthogonal to all Z's. Sorry, that is orthogonal to all Z's, right? Yes, that is correct. So you could make sense of it however you like, but I could go into a bit more detail with this later on. So we get a system of equations and we solve them linear algebraically, with linear algebra, and that can be done with Gaussian elimination. And you know that Gaussian elimination you would need to operate this, you know, in a way that gives you the pivot points to be 1, 1, 1 in a reduced echelon form. So you'd get variable values with x1 equals to something and x2 equals to something, essentially giving you this vector, where multiplied with this matrix Z, you get the null space, right? Or you get 0, and these are the solution to this problem. So right, so now we have found this, right? We have also another way of doing this, but I'm going to explain that to you later on. Now here he has done the example here. I'm going to go into a bit more detail here. Let's say, right, so the third step, it's right, the example was right here. So now it's saying that our secret string was 1001, and now the first step is going to have n qubits of equal length on both registers, right? So since this is 4 qubits, you get 4 qubits in the first register and 4 qubits in the last register. And now these are in tensor product form. And we have devised a function where we have, since this is a 4 qubit, right? So you'd get 16 inputs, 16 possibilities, 2 to the power n, right? And these are all the 16 inputs. And for these, it has calculated an output. Now, because 2 of these inputs have the same output, these are put in the same column. Sorry, the same row, right? So you have essentially 8 possibilities that corresponds to, you know, a pair of input. Now, in the second step, it has applied the Hadamard gate, and we get an equal superposition. And once you expand this X, you get, as I said, probabilities of, you know, the states that are contained in that n qubit space. And then the third step is going to be right, is to have the function transferred over to the second register, right, leaving the first register unharmed or untouched, right? Then again, you'd have, you know, x's and f of x, right? This corresponds to the first register, this corresponds to the second register. So as you see, these are correlated, right? Let's say we measure 111, right? for the 111 output f of x, right, it must be the case that we get 0 0 0 in the first register. This is what I was talking about. And if you have a 2 to 1 function, instead of just getting 1 1 1 corresponding to quadruple 4, you get two of these, so like 0 0 0 plus 0 0 1 1 or something like that in equal superposition. That corresponds, so both of these corresponds to the same output, so you'd get a quadruple 1 at the output, right? But that's just me getting ahead of myself. So what we have now is an equal superposition here. Wait, is that equal? I'm not sure, because for equal superposition this has to be raised to the same power or something like that. So anyway, well, equal superposition can be found out by dividing it by the norm, and you can calculate it. I haven't done that yet, but that's a good question. Are these in equal superposition? I'm not sure, really not sure. Now we measure our second register. Well, we could just check, right, for equal superposition. Right, you have to have all of the probability amplitudes summed up to 1, right? And if all of these probability amplitudes do sum up to 1, because all of these, as I see them, are in pluses, none are in minus, but there has to be some that are in the minus state. Anyway, so now what happens is that we measure the second register where it contains the f of x, right? So we measure what kind of things we get, and we get a corresponding x and x XORed with b. And see, we get two values here. So essentially we get quadruple 1 and 0 1 1 0. These are the ones that are defined in the table, and we get them corresponding to 1 0 1 0 1 0, right? So now these are the two inputs that we really need, so we ignore the second register. Now we apply the Hadamard again and see our x in this case is going to be 0 1 1 0, and z is going to correspond to 1 0 1 0. Is it? No. Z are going to be the summation that is generated by applying the Hadamard gate, right? So because of 0 1 1 0, so because this is a 4 qubit state, you'd get like 0 0 0 0 0 0 1, so like 0 1 2 3 till 16, right? So you'd get 16 terms here, I think so, right? 2 to the power 4 is 16. So you'd get 16 terms here and 16 terms here, with each of them having equal amplitudes, so equal occurrences of positive and negative terms. Now if these are equal, why don't they just all vanish? But that's a question, and I have to look into it. So -1 x dot z and then -1 y dot z, right? Once you evaluate that, you get essentially such kind of state, right? Did I jump right there? I think I did. So they haven't yet applied the Hadamard gate, but how did they get this? So you're getting the superposition here, sorry, I mean summation here. I think I'll have to look into this a bit more, because I don't know how the summation came here, because we're not applying anything. So psi 5, you see psi 5 is somewhere here, psi 5 is somewhere here where we are applying the Hadamard gates, right? We are applying the Hadamard gates, so that's why the summation is there. I was just confused because of that. So once we get that, of course we have the same drill, and what we have is we basically expand that in the next steps. And now you see that we have pluses and minuses, right? And these are the z's that you actually get. Now for these z's, we have a system of equations where b dot z equals 0, and we get 8 such equations because we have 8 such bits that are unknown, right? So z1, z2, z3, z4, and these are not the thing I am referring to here, because z1 refers to the equation 1, right, and z2 is the output, second output or the third output. So whenever, so like in our first attempt we get z1, in our second attempt we get z superscript 2, and then z superscript 3, so on, right? But what I'm referring to is that z is some kind of vector where it contains the elements of dimension n, and n has to be equal to the number of qubits in our secret string, or in our quantum circuit, right, of n size. So if we have a 2 to the power 4, right, if we have a 2 to the power 4, we'd have a string of 4. And how many unknowns should we have? We have 4 equations and 4 unknowns, right? That should be it, but now it has 8 because of qubits being there are 3 qubits now. Are there? No, there are 4 qubits. So a 2 to the power 4 would have 16, and then 16 outputs. Do I see 16 here? I think it generated 16, but then because of the equal amplitudes, some of them were cut down, so now we get this, but we get 8 equations here. That means there has to be 8 unknowns here, right? Now why are we getting 8 equations here? It doesn't make sense, really. So it says we need here at least 3 linearly independent values of z to find b. Now that's the next step, and we're going to go there, but I was wondering why this is in the first place generating this, because this is 2n plus 1, right? So n is going to be 4, right? N should be 4, because these are the secret string contains 4 of elements. So now 2 to the power 4, this becomes 2 to the power 4 plus 1, or we could expand this as 2 to the power 3 multiplied by 2, right? So this becomes square root of 2, right? I think this is essentially what I was talking about, that it's going to be 16 inputs, but through some calculations here it has written 3 here, which I'm not sure yet. I'll have to look into it. So we get 8 8 values and 8 unknowns, and the secret string then has to be of length 8. How could that be of length 8 when wait, does it? I mean, 8 is the times that it has run, right? So it has run 8 times. It doesn't necessarily have to contain 8 values, right? We only need 3 linearly independent values, so like values that cannot be recreated by having some kind of combination with each other, right? So as we see that 0 0 1 0 and 0 1 0 0 and 1 0 0 1 cannot be generated by adding or subtracting them. So these are linearly independent values, and so what happens is that the fourth one we choose to be 0 0 0, and in that case essentially we do have 4 equations and 4 unknowns. So yes, I'm correct. Yes, so we have 4 equations, 4 unknowns, right? So as we see here, right here, right? And so now here is the matrix, let's call this A, and the secret string having elements of B to be a vector B, right? And these both equal to 0 when multiplied. So we can do this by elimination method or Gaussian elimination. Both of these work, and there is also another way by brute forcing it, right? So a brute force would be to have to generate all the possible strings that are inside that are possible because of having n qubits, right? So 2 to the power n. say n equals to 4, then there are 4 possibilities. And what we do is that we check the dot product with all of the outputs in each run, right? We get all of the outputs in each run. Sorry, we get all of the we check the dot product with each of the z's, with each of the outputs, right? So linear algebra is not yet involved here. That is the other step, which is seen right here. But what we do in the brute force method is that we have the output, right? And then we have the possibilities that we generated before. So we dot product each of the possibilities to all of the outputs that we get for a certain attempt, right? So let's say we are in our 4th attempt. So we would get, let's say, 9 values, right? Let's say. So in that case, so 9 states, you have to check by having them dot product. So let's say we get in our combination 0 0 0 1, we'd get the combination 1 1 1 0 1 1 1 1 and so on, and you have to check the dot product. The string which lies in the possibilities that we've just generated, the string which is orthogonal to all of the possibilities, so all of the outputs that we have gotten for a certain run, is our secret string S. And that is essentially what it's doing in linear algebra, is that it has to be orthogonal, and that is our solution. Now I think this is enough for me here. In the next video I'm going to attempt the programming part of it. I have already the code here which I'm going to show you, but let's do that in the next video. That got a bit confusing because I confused myself a bit, so definitely if you're just watching this with some tea in your hand, in your hands, that's good. But I'm not a professor or anything, so take your time, do your own research, and let me know if you have any questions. Thanks.